All right, everybody. Welcome back to Track 3 Cloud of Python WebConf 2021. My name is Josh Qualls. I am the Loudstorm account manager here at 6 Feet Up. Today, I am joined by Suman. He's going to be talking about PyTorch and NLP models using Amazon SageMaker and Amazon Elastic Inference. I love talking about SageMaker. Those talks are always very, very interesting to me. So I'm very excited for this presentation.
Thanks, Josh. Hello, everyone. Good morning, good evening, depending on from where you are joining. I'm super excited to host this session, and this is the second year for me at Python Web Conference, and I feel extremely privileged and lucky to be with all of you. So let me first share my screen. At any point in time, if you have any questions, feel free to ask in the chat, and we will also discuss a few of the questions if time permits towards the end. And feel free to reach out to me at later point in time via LinkedIn or Twitter, whichever medium that you feel like, so that we can take this discussion forward. My objective is not to complete this presentation or demo in 20-30 minutes, but to connect with you so that I can be a part of your learning journey. Okay, so having said all of this, today we are going to talk about NLP model, specifically using PyTorch and using BERT, which is one of the latest and greatest model architecture we have in the field of natural language processing. So myself is Suman Debnath. I'm a developer advocate. I'm based out of Bangalore, India. And I joined Amazon roughly around 2 years back. And I predominantly focus on data analytics and machine learning. So with that, let's try to understand what is NLP. So there is some prerequisite for this session in the sense that if you are coming from machine learning background, it's good. You can connect the dots. But even if you are new to machine learning or you are new to NLP, that's completely fine. We will try to touch base on the basic concepts first before we dive into the demo using PyTorch. So if you look at the machine learning problems in the field of natural language processing, which is nothing but a kind of a subfield between linguistic and computer science, where we humans generate a lot of complex sentences or complex languages to interpret. Like I am speaking to you now, you are able to understand, right? Because you understand English, you understand how a human talk, so you can get that context right. But think about how how a machine can be trained to understand that language, right? So that is very difficult, and we have many different use cases like text classification, speech recognition, text summarization, and these all things we use in our day-to-day basis, right? If you pick up your phone, maybe after this session, if you type a message to someone, you will see that the moment you type the first word, the second word automatically comes in your keyboard or in your display, right? In your mobile phone or in your laptop. And if you click on that, you will again get the next word. So how this is predicting, next word, one after another, while you just start with your, first letter. So these are the things that, or the architectures that we are going to discuss today are the driving force behind all of these revolutions, right? So the idea is to make a mathematical representation of a language to solve all these kind of problems. So whatever problem that we discussed, like text classification or speech recognition or text summarization, these are all classical NLP-based problems. And what we need to do is we need to come up with a mathematical model so that a computer can understand, or rather, in a specific way, you can train a model in such a way that it can solve or it can predict all of these problems. Now, there have been a lot of research and work going on for quite some time. Like we used to have Word2Vec, Glove, FastText, and all of this. But the revolution has actually come in in 2017 and 18 timeframe with the introduction of transformers. Just to give you some background, how these kind of problems used to tackled before 2017 is still today we do use. So basically, there are few algorithms or networks you might be aware of called RNNs. then GRU, then LSTM. So these all are based on a recurrent neural network, where given a sentence, it used to take one sentence at a time, and one word at a time, and it used to try to predict the next word in that sentence, right? So it used to go from either left to right or right to left. So these kind of networks or models are not very good when the sentence length is very big, right? Because when you come to the last word of a sentence, which comprises of, let's say, 500 words, you actually lose the context of the first 400 words, right? So that's why these networks are not that popular these days, and people are mostly focusing on transformers and BERT. So before we get into transformers and BERT, let's try to understand why transformers. So if you look at this, these two sentences, the bat flew past my window, and there's a other sentence, he hit the basketball with a bat. Now, we as a human, we understand the context of these two words, bat, are completely different, right? So, but if you consider this with the traditional way, the way that we used to use to embed these sentences, the meaning of bat, right? The meaning of bat here and the meaning of bat here would be completely same, right? If we use something like word to vec. So you can imagine word to vec as, let's say, consider as a list where you have bat, and the bat will have some vector representation, and then maybe the word he will have some vector representation, and no matter, and so on with all these sentences, right? So now, when the word to vec receives a sentence and it need to convert this bat into a vector representation, or you can imagine vector representation as just a array of numbers, and because bat is an English word, right? And we don't computer do not understand any words or anything of that sort, so we need to represent that in numbers. So when we think about word to vec, whenever it receives something called bat, it will just go and search, in its hash, and whatever is the vector representation, it will just, have that. So it will not have the context that the bat is representing in the whole sentence. So that was the most difficult part in word to vec, or the traditional way when we used to do NLP based problems. Now, another thing that we just discussed is about bidirectional context, because most of the older architecture like RNN, LSTM, those all are bidirectional, and that doesn't help always, right? Because a lot of time the context come up when you actually hear the whole sentence. So let me give you an example. Let's say my manager tells me, "You did well," and now you don't know actually what that well actually signifies, right? So let's say if I say you did well, that's why we are giving you 20%, let's say, bump in your compensation. So this becomes a positive sentiment, all right? And you could figure it out when you actually heard the whole sentence. But now, let's say if I say something like this, you did well, and then the following phrase would be, let's say, you did well, but others in the team did much better than you, so I'm not very happy with you. So now this sentence have a negative sentiment. Now, if you use a traditional model to detect the sentiment of these two sentences, you may not get the right answer, because those models or architecture read word by word and one after another in a sequence, either left to right or right to left. So you will not get the full context of each particular word with respect to the whole sentence. And that is what is solved by something called attention, by transformers, and which was introduced in a paper called Attention is All You Need. So this is the research paper which came up in 2017. And that changed the whole ballgame of NLP in the industry. And all the models that we see today, like BERT or other models, they all are kind of motivated from transformers. In fact, BERT is you can think of it as a special type of a transformer. And the way that BERT or transformers differentiate with the traditional approaches is by having a context-based embeddings. Like if you look at this sentence, the movie is funny, it is great. Now here we know that it can represent movie and or it can be funny or it can be great. So the way that transformers it makes a representation is it reads through all the words in the neighbor in the whole sentence, and it tries to find out on which part or which other words have its or relationship more. So like in this context, it has this, it represents the movie, right? And the most importantly, this the it representation, the representation of this will contain the context of the whole sentence, right? So that's the beauty of transformers. And how it does that is using attention, right? And it is it's very simple with respect to if you compare it with neural networks, but it's little math heavy, so we are not going to go over the theory of maths and all of this. But if you are interested, I'll be very much happy to explain you offline. But the idea is the whole purpose of transformer or BERT is to have a better representation of your whole sentence, right? So you will start with some encoding of each and every word in the sentence, but at the end of the day, when the transformer or BERT actually predicts or rather we are going to see that in the next slide. But at the end of the day, transformer and BERT, whatever you pick, they will give you a better representation of all the words. So let's try to see, how BERT works and what is inside BERT. So this is introduced in 2018, and it has a pre-trained model, and we will discuss that what is pre-trained in a minute. But this has been trained on a huge data set using Wikipedia data and the book corpus, which contains more than 800 million words. So this has been trained with a lot of effort, with a lot of compute resources. So you don't have to train it from scratch to solve your problem. And we are going to see that how you can use BERT and make some fine tuning to work for your specific problems. Okay. So let's see how BERT actually works. So before we get into BERT, I just want to point out one small thing. Is initially, when we started this presentation, I mentioned that BERT is a special type of transformer. And the reason that I said that, because if you look at transformer, you will have something called encoder section, and then you will have something called decoder section. Okay, and whatever so it takes a sentence. Let's say this is the input, right? And you can consider this encoder as a black box as of now, but it gives you a better representation of the input as the output right here. So, and this output is fed into the decoder, and then decoder is the prediction or the output of this whole model. So this is the final output. Okay, so basically you have an encoder part and a decoder part, right? But in BERT, what happens is you don't have this decoder part at all. So all you have is the encoder. Okay, that's why we typically say that a BERT is a special kind of transformer which doesn't have the decoder, right? So that's why the name is like bidirectional representation of transformer. Okay, so encoder representation of transformer. So now let's look into BERT, how it works and what it is from inside. So now if you look at the BERT, it comprises of multiple encoder layers. So we talked about this whole thing is an encoder. Okay, and inside that you have multiple encoder layers, and all of these layers are actually identical. And what it does is, you feed your sentence as an input, and these are nothing but your words. okay, in the sentence. So it can have 512 words at max, or you can actually have more. But in the research paper, they max, I guess, they used 512 words in a sentence, which is quite huge. Now you take all these words and you feed into this network, and inside this encoder, each encoder layer, you have something called attention layer, okay, and feed forward neural network layer. And this is common in all these layers. Okay, this is common in all these layers, and the architecture is such that it takes the input here. Let's say the layer one will take the input from the user, and the output will be feed into the layer two, and this process goes on till the last layer where it gives the output, right? And at the end of the day, we start with some embeddings, right? Let's say the sentence is, "I love Python." Okay, so I will have some embedding for these three words, right? But at the end of the day, when we get the embedding of these three words, that would be a much better representation of "I love Python," because in that case, those three words will be having the context. Each word will have the context, with respect to the whole sentence. So, and we are going to see that, what is this blue box? This is a special token that is always added in the beginning. We call it as a CLS, and this is a special token that we need to add in the front of every sentence. Now, the way that the BERT works is that it uses a pre-trained model. And why we say pre-trained? Because at the end of the day, the idea is to make a model which can understand a language better, right? And the way that we can make a language better is by solving some problems, right? So BERT is trained for these two problems. One is masked language prediction, and one masked language model, and another is next sentence prediction. Now, what are these two different problems? If you look at the image on the right-hand side, you see that there are two sentences, sentence A and sentence B, right? And the idea is when BERT was trained, rather pre-trained, it need to solve these two problems simultaneously. And the way that it used to solve this is by masking few of the tokens in the whole sentence, because the masked language model is nothing but, given a sentence, we will mask few of the words, and at the end of the day, the BERT should be able to identify those masked words. So if I tell you a sentence, and if I give you some fill in the blanks, and if you are able to fill those blanks, then I can tell you that, okay, English much better, or you have a very good understanding of English language because you are able to fill in the blanks of the sentence that I'm giving you, right? So this is the problem that it need to solve. And the next problem is next sentence prediction, and that means that when it is given with two sentences, it need to figure out that sentence B is actually coming after sentence A or not, right? So let's say you give two sentences, and those two sentences are one after another, then the model should predict that these sentences are one after another. So it's kind of a binary classification, and this this classification is given by the first representation of CLS, and that is nothing but this one. And it can be, let's say, 0 or 1, where 0 means okay, sentence B is actually sentence B is it comes next to sentence A, and let's say 1 means they do not come next to each other, right? So the idea of BERT is when it tries to when it was trained initially during the pre-training phase, it took all those sentences in the from Wikipedia and all of that, and then the idea was to solve these two problems, masked language model and next sentence prediction, right? And once these two problems were solved, we can make use of this model for fine tuning. That means we can make use of this model to solve our problem. So one of the example would be, let's say, question and answer, right? So you can think of this as you give one question, Okay, and you give all the, let's say a question comprised of 10 words. So all those words will have 10 tokens, and then you have a special token called SEP, which is nothing but separator. And then because you need to, the model need to identify where the question ends and from where the paragraph starts. And then you have the, paragraph. Now, the problem that we are trying to solve is we need to figure out that the question can be answered, or the answer of this question lies inside that paragraph or not, right? So that is the problem that we are trying to solve. And we can always use the pre-trained model, and we can just fine tune it. Now, what do we mean by fine tuning? What we can do is basically this question's tokens will have a better representation here, right? But we don't care about all of these representation. But all we care about is the representation of this paragraph tokens. And let's say this paragraph contains, let's say 500 words, right? So I will have 500, tokens at the output here. But all I'm interested to know is the start of the answer and the end of the answer. So let's say this question had an answer inside this paragraph, and it starts at, let's say, 110th word. Okay, and the answer ends at, let's say, 112th word. Okay, so the output of this representation, we can put a classifier on top of that, a binary classifier, and we can use, let's say, something like softmax, so that every token will have a probability of start and end. So let's say word number 110 will have the maximum probability of this being a start word, and 112 will have a maximum probability of being an end word across all those words in that whole paragraph, right? And we can solve that problem using BERT. So this is what we call it as fine tuning. So when we combine these two, right, pre-train and fine tuning, we actually, you can think of it as a transfer learning, and we can use it for various things like sentiment analysis. So given a sentence like "you are awesome," and we know that this has a positive sentiment, what we can do is we can use the classifier. We can put our own classifier on top and take the representation of CLS, because we don't care about all of these representation, because we are not going to do anything with this whole sentence. All we need to know is whether it is a positive sentiment or negative sentiment. And we can use the CLS representation, because we know that in this BERT layers, we have in this all encoder layers, we use something called attention, which takes the representation of each token with respect to the whole sentence. So CLS representation is actually have the information about all these words, right? So it will have the representation of all these 3 words, right? So that's why we say that you can use BERT and you can put your own classifier on top, and if you can train that, you can solve your own problem. And that is what we can do for other problems, like, let's say, name entity recognition, where you need to identify each and every word, whether this is a noun or a verb or whatever. So in that case, you don't care about this representation, but all you care about this, each token's representation, and you can put your own classifier to determine the entity, right? So all you are doing is you are making use of this pre-trained BERT model, and you are just fine-tuning it. And PyTorch or Keras or TensorFlow all have their libraries to help you to do this task. Okay, so in this now we will jump into the demo, and in the demo, what we are going to do is we are going to do a very simple fine-tuning for grammar check. So given a sentence, we will try to classify whether that sentence is grammatically correct or not. So in this problem also, it's just like sentiment analysis, where we don't care about the representation of all these tokens. All we care about is the CLS representation, because grammar check is again a binary classification. Like it can be yes or no, like grammatically correct or wrong. So we can just use our own classifier on the top, and we can say that the class labels are 2 because it can be yes or no. And we can just check the grammar. Okay, and we are going to do that on SageMaker, and I'm going to show you that how you can do it effectively using Elastic Inference, and I'll show you in the notebook itself. All right, so let me jump to the demo. So this is SageMaker. So if you're new to SageMaker, SageMaker is basically the machine learning service from AWS, where you can build, train, deploy your models, easily. So I came to this notebook directly, but if you want to go to SageMaker, you can log into AWS console. You can search for SageMaker. Okay, so I have already opened it, so I'm just closing this. And you will see all these, different features and capabilities of SageMaker on the left-hand side. And there is something called Notebook, and you can click on Notebook instance. And here you can click on Create Notebook instance. So it is just like a Jupyter notebook that you use in your laptop or in your desktop. But the beauty of this is when you create a Jupyter notebook instance by clicking here, you can give some name, you can give the type of instance, and all this type, represents different number of virtual CPUs, GPUs, memory, and all of that. You can check the documentation and pick the right model of the instance. And then you can just create this instance. And what happens is once you create this instance, you can just open the Jupyter notebook like this. And this is not the home page, but if you just click on this, you will get the welcome screen, and you can create it's just like a regular a Jupyter notebook. But the beauty is when you come to new, you will see all those kernels already available. So you don't have to install, configure anything of that sort. MXNet, PyTorch, TensorFlow, everything is installed. And it has a very nice integration with other AWS services. And we are going to see that now. But I would highly encourage you to make use of Jupyter Notebook on SageMaker. All right. So for this problem, we are going to use PyTorch. So we are just installing PyTorch, and we are installing transformers. This is a library which is from a company called Hugging Face, very popular in NLP. And in fact, yesterday only we announced a collaboration work with Hugging Face. Now you don't have to install it separately. It would be a part of SageMaker SDK itself. So feel free to try that as well. And I can convert this notebook to use that because it just launched yesterday. I just thought, not to use it. I'll convert this as a second version. You can check it, check the, Git repository. All right. So first is we need to import a few of the libraries like SageMaker, NumPy, Pandas, a general thing. And here we are creating a session, and we are creating a bucket. So we are using an S3 bucket for this. So S3 bucket, if you're new to AWS, is you can think of it as a kind of a Dropbox where you can just dump your data, and it can do a lot more than just dumping the data. But Amazon's have a service called S3, which is an object-based storage, where you can create your bucket and you can put your data inside that. So this is the bucket that we are going to use. And this is the prefix that we are going to use, so that everything, whatever we do, it would be under Python Web Conference 2021/demo PyTorch BERT. Okay. And then we are going to download the dataset. This is for grammar check. So we are downloading this dataset from Linguistic Acceptability Forum. This is an open source dataset. We are just downloading it. Nothing very fancy here. And then we are trying to load the data using Pandas. So we are just reading this CSV file, and this file contains a lot of fields, and we are interested into only the label and sentence, where the label says it's grammatically correct or wrong. So if it is 0, then it's wrong. If it is 1, then it is correct. We are just printing it using the last 5 sentences by using df.tail method. And this is just to randomly see 5 sentences and 5 labels. Okay, so because we are saving the sentences and labels in a separate variable here. Okay, so we are just printing it just to check, and we are just exploring the data set basically. Okay, so the first thing that we need to do is we need to split the data for training and test. This is a general practice for machine learning. We first split the data. So by default, the split ratio is 75-25. For test split train test split method inside this scikit-learn model selection package. So we are just splitting the data, and we are saving the data into CSV. Okay, so this is just for loading the data. We already loaded the data in the data frame, and now what we are doing is we are just splitting the data for test and train. And then we are just uploading this data into our S3 bucket, because we are going to use SageMaker for training. Before we go down, we are not going to train in this particular notebook. So this is the beauty of SageMaker, that this notebook is just for you to write code, and create the models and all of this. But we are not going to train the model on this particular instance, right? Because our training might need hundreds of GPUs, hundreds of CPUs. So we cannot just use that machine for our day-to-day work, right? And we will see that how SageMaker can help you to do so. Okay, so that's why we are loading the data into S3 bucket, not in this particular notebook instance, because we want the SageMaker to go to that S3 bucket and read the data while starting the training. Okay, so this is the problem. Just to summarize, where are we, and what we are going to do is now we are going to train the model, right? So now we are going to use a training script, and this script is present in under this folder called code. Okay, in the present working directory. So we have a script called train and deploy, and we are going to use transformers, right? The library that we just mentioned. And there are a few things that I want you to show. You see that the max length is 64. That means this is the maximum length of the sentence. Like in BERT, in the research paper, they used, I guess, 512. So in this example, we are just putting this max cap of 64 length. Okay, so if any sentence comes which is less than 64, it will use a special technique to pad, keep a extra padding, just like a special token we have seen, like CLS and SEP for separator. Similarly, we have a special token for padding. So it is called pad. So it will do that if any sentence is less than 64. Okay, so one interesting thing that I want to show you is how we fine tune, because we are not training it from scratch. We are going to fine tune the model using BERT, right? And that's why if you come here under training, if you come here in this line, right? If you see this, we are using BERT for sequence classification from pre-trained. That means that we are going to use a pre-trained model of BERT, and we are going to fine tune that. And since our problem is a binary classification problem, we are just putting the number of labels as 2, because this is the variable that we are setting, outside this function. It's coming as an arg, and the number of labels is going to be 2 in this particular problem, right? And there are other parameters that you can set, like output attention, output hidden state. Like if you remember, we mentioned this right in the presentation. Let me switch back. When we do this classifier, we don't care about all of these representation, right? So, and we are not interested in the representation of each of these 12 layers. But transformers or Hugging Face library gives us the capability to even read those outputs. So here we are putting it all false, because we are not interested in that. We are just interested in the last classifier. Okay, so this is the most important thing as far as the fine tuning is concerned. And rest of the code is pretty straightforward, a regular machine learning pipeline. You take the data, you do some pre-processing, and you just start the training. Then you propagate, calculate the loss, and minimize the loss. So we're not going to do that, go over line by line. But one important thing is, once the training is done, we are saving the model artifacts into S3 bucket. Okay, so that is what we are doing here. We are just saving the model into a directory called model directory, which is defined when we start this script. Okay, so two things we are doing. We are training it using a pre-trained model, and we are saving it in S3. Okay, so let me scroll down and just come to the next stage. So now we have just walked through about with the code, right? But now we are going to actually start the training. So as I mentioned, we are going to use an estimator. So we are not going to training in this particular notebook. And the way that you can do so using SageMaker is using an estimator. So what is an estimator? There are different estimators that we have in SageMaker, and you can import like this from SageMaker.PyTorch, import PyTorch. If you are trying to create an estimator for PyTorch. So what it will create is, it will create a virtual instance or a container based on the configuration that you provide. And it will take the code if you have given any code, and it will do the training there. And once the training is over, it will save the artifacts in a location which you mentioned at the start of the training, and it will just destroy that instance. So that means that if the training runs for 5 minutes or 5 days, you'll be charged only for 5 minutes or 5 days respectively, right? So that's the beauty of estimator. So we are defining the entry point because we want this particular code to run, and we are defining where this code exists. Then this role is for security. We have defined some role, so that because SageMaker need to read data from S3, so we need to have permission granted for SageMaker so that it can go and read from S3 bucket. And that's what the role is defined. Then we can define the Python version, and here we define what type of instance we want, right? So if you want multiple GPUs or multiple CPUs, you can just check the documentation. Whatever is the instance type you want the training to happen, you just mention that. And here we are doing a distributed training, for distributed training we need to have more than one instances. So we can define the number of instance count. So if it is 10, the training will happen parallelly in 10 instances. And then there are some hyperparameters that we are giving, which is specific to this particular algorithm, right? So we are going to use BERT, and for this particular problem, right, which we defined inside this Python script, it contains two labels, right? That's why the number of labels is 2, because this is a grammar check. It's a binary classification, so we are defining as 2. And backend is for CPU instance or GPU instance. So you can check the documentation which one to pick. Okay. So once this is done, we can just start the training with estimator.fit, and we can give the training data and the test data, which we actually saved while we split the data into training set and the testing set, right? And now this training will take some time, and I already executed. If I scroll down, you will see how much time this training took, and it will also tell you what is the accuracy. So it got roughly around 82% accuracy, which is not that great, but given the number of sentences, I guess we have in this particular data set roughly around 10,000. It's quite reasonable. Okay, so this took 600 seconds, 650 seconds roughly. So you'll be charged only for 650 seconds. That's all. Okay. So once this training is done, we need to deploy that, right? So that we can do some prediction. And the way that you can deploy is using estimator.deploy. And again, for deployment, you can even say what type of instance you want, right? Because for inference, you don't need a very, a high-ended GPU or CPU, right? So you can define the instance type. So in this case, if you look at it, the instance type is different with respect to the instance type we use for training, right? And once you do that, then we can just use some serializer and deserializer so that we know that how to parse the data, and then you can do a prediction. Like you can give a sentence, and you can give the you can get the class prediction. Okay, so we are just using NumPy argmax, so that because our classifier will give us the output, right? So if you look at if I just go back to this, the final classifier is the binary classifier, right? So it will give the probability distribution with across the two outputs, right? Yes or no, and we can just pick which has the higher probability, right? And we use argmax for that. So this is the maximum in these two numbers. So we know that this is a positive. It's a correct sentence, grammatically correct sentence. Okay, so now what we are going to do now is, we are going to use this model artifacts for deployment. So now you can always delete this endpoint using predictor.delete endpoint, right? I have not deleted that, but you can always, you should delete that once your work is done. But let's say now you want to deploy this model using the model artifacts. So we have saved this model artifacts in this S3 bucket, but now you want to, load, you want to deploy that. Okay, forget about this notebook. If I just give you this path and give you enough access to this S3 bucket, how you can just deploy that. Okay, you are not training it, but the idea is you are going to deploy or use a pre-trained model. How you can do this? You can use a PyTorch model functionality. So you can again import it from SageMaker. You can give the PyTorch model, and then you give the model data. Okay, here we are not giving that script. So we are giving this model data. This is the path of this data, and then we defined all these parameters and the script. That's all. And then again, serializer, deserializer, you just have to set, and you can just do the prediction using predictor.predict. Okay, so this is how you typically do a prediction in a normal case. But there are instances where you need to have a GPU for inference, right? Because not always, CPUs are useful, because let's say you have to, your inference need to do some matrix multiplication, very complex computation. In that case, CPUs are not very good for matrix multiplication and any of the arithmetic operation. So in that case, you might need a GPU. Now imagine you deploy a model for inference in a GPU-based instance. So the cost is pretty high, right? So if you look at this cost of any GPUs, which is in the right hand side, it's pretty expensive, right? $14 per hour, $28 per hour, $1.125 per hour. So you can see that it's quite expensive. So that's why we suggest developers or users to use something called elastic inference, where you can make use of GPU on top of your existing CPU instances with a fraction of cost, right? So what you do is, in place of specifying a GPU instance, what you say is you will deploy it on an elastic inference instance, okay, along with your CPU instance. And we are going to see that how you can do so. But if you see these instances which can give you GPU power to your inference, are very cheap, right? It's less than 10 cents or 30 cents, right? So you can always make use of that to get even similar performance if you have deployed this model on the GPU. So the only thing that you need to do is there's a little change that you need to do, because for this you need to convert your trained model into dot script. There is a beautiful blog post which I was reading a couple of months back on dot script and how it works. And to know more about it, you can just refer to this, or you can pick up any literature. But we need to modify a little bit in our code when we use elastic inference. Okay, so I'll just quickly show you the difference where we need to change. So here we are not using that same script. We are using a deploy_ei, and this is because there is a subtle change in the script with respect to the trained deploy script which we have used. And the difference is this. Let me scroll down and show you that. So this code will be given to you. You can always make use of that and build on top of it. So the way that it uses torch.git, and then we use an optimized execution, and we mentioned that it need to use some GPU. So EIA represents the elastic inference, and 0 stands for the GPU. So what is a target device, right? So this is the only change we need to make in the script. That's why we modified the predict functionality with respect to the predict functionality that we used in the earlier place. Okay, and rest of the things is all same. We use a PyTorch model. We give the model name, and now we give this entry point, and we also define where we define the instance type. Yeah, here we define the instance type, and if you look back, this is the instance type we are using. So the instance type is MLM5 large, and we are using an accelerator type of EI A2X large. Okay, so you just have to define these two extra parameters, and that's all. And then everything remains the same. You do a serializer, deserializer, and you can just do the prediction. Okay, and you get your prediction from this, from this model. But what is happening now is, you are charged less with respect to before. Okay, so with that, I'll stop. And if you have any questions, feel free to ask. If not, then feel free to get into the GitHub repo. I can share the link, and ping me anytime if you have any questions on LinkedIn or anywhere you feel like.